Welcome to Lesson 1, Simplify Rational Expressions. So now that you are very good at factoring polynomials, you are going to use those skills when you're dealing with rational expressions. Especially today when we start to simplify rational expressions. Our objectives are to write a rational expression in its simplest form by eliminating common factors. In order to find common factors, we will need to factor first. We will also identify values in the domain that would make the expression undefined. Very important. Here's an example of a rational expression. We have a numerator, we have a denominator. Notice that both the numerator and the denominator are polynomials, which you've been dealing with extensively. Okay, let's consider how we would simplify this. So right now you should be thinking, oh, well, I would figure out what goes into both 60 and 75 and I would reduce. And that is exactly correct. That's what we're going to do. So let's walk through that. Well, let's go ahead and factor the 60 first. So if I factor 60, I know that 2 goes into 60, and that's 2 times 30. But then I need to factor the 30. So a 2 goes into 30. Goes into it 15 times, but I can also factor the 15. 3 goes into 15, and it goes into it 5 times. So now I have completely factored the 60 into all of its prime numbers. Notice that all of these numbers are only divisible by themselves and 1, just like when you were working with GCFs. Now let's do the same thing for 75. Okay, when I think of 75, I think of 25 times 3. So I'm going to write the 3 right here and the 25 here because I know that 25 is not a prime number yet. 25 can be found by taking 5 times 5, and I know that those are prime numbers, so I'll go ahead and write them there. So now I have broken apart the 60 and the 75 into all their primes. So let's go ahead and simplify. So what that means is I'm going to cross off everything in the denominator that I see in the numerator. So I can cross off the 3's. I can cross off the 5's. And now I just need to write what's left. So I have 2 times 2 left in my numerator, and I have 5 left in my denominator. Now I have reduced this fraction, or I have simplified it. And that's what we're going to do with these rational expressions with a polynomial in the numerator and a polynomial in the denominator. So if I look at my numerator on this second one, x minus 1, I can't factor that anymore, so I'm going to leave that as x minus 1. If I look at my denominator, I think, okay, it looks like I have a GCF. It looks like there's both, there's a 5 in both terms. So there's a 5 in the first term, there's a 5 in the second term. So I'm going to factor that out and then write what's left. 5x divided by 5 just leaves an x. And negative 5 divided by 5 just leaves a 1. Okay, I have completely factored my numerator and my denominator, and now I just need to cross off what's in my numerator and in my denominator. So it looks like we have x minus 1 in both. Now remember that I can't just cross off an x separate from 1 because this is an expression. It's connected with a minus sign. But I can cross off the entire x minus 1 in the numerator and the entire x minus 1 in the denominator. So what's left? Well, if I've crossed off my entire numerator, then I'm left with a 1. In my denominator, I'm left with a 5. So this polynomial, this rational expression with 2 polynomials, simplifies into 1 over 5. Let's go ahead and do the same thing now for our last problem. Again, I look to see how I can factor my numerator, and it looks like I have a GCF of 3. So I'm going to factor out a 3 and write what's left. If I factor a 3 out of 3x, I get x. If I factor a 3 out of minus 6, I get 2. Actually, I get minus 2. Now my denominator is going to be a little more tricky. If you'll notice, this is a quadratic, and as soon as I see that, I think, oh, maybe I can factor by grouping. So I would take the coefficient of the x squared term, which is 1, times the minus 6, to write minus 6 on top, and then the coefficient of the middle term, which is just 1 down here. What times what is negative 6 that adds to be positive 1? That would be 3 and negative 2. So now I know how to split apart my 1x. All right, I'm going to go ahead and write my quadratic. Here we go, and now I'm ready to group. So I have my first group and I have my second group. In my first group, I can pull out an x, leaving x plus 3. In my second group, I can pull out a minus 2, which also leaves x plus 3. Now from these two groups, I have an x plus 3 in both, so I'm going to factor out an x plus 3. And that leaves x minus 2. So this is how my quadratic has been factored. Let me go ahead and write that down here. So I have x plus 3 and x minus 2. Now I have factored all my polynomials in this rational expression. I've factored my numerator and I've factored my denominator. Let's go ahead and eliminate anything that's both in the numerator and in the denominator. So it looks like we have x minus 2 and x minus 2. We can eliminate that. Again, notice I can't take the 3 and eliminate it with the 3 because this bottom expression is not 3. This bottom expression is x plus 3. It's combined. It's one element. So I can't take pieces out of there. So what's left? In my numerator, I have a 3. And in my denominator, I have an x plus 3. Okay, now I have simplified all of these rational expressions. Let's now go ahead and talk about domain. What I want you to consider is what would cause these functions to be undefined. So I have these two functions here. What would cause them to be undefined? Hopefully right now you're thinking division by 0. If we have division by 0, we have a problem. We cannot divide by 0. If we have a 0 in the denominator, then our function is undefined. So all we have to do to determine what would cause these functions to be undefined is set the denominator equal to 0 to see what would make it equal 0 and solve. So in this case, we would add 5 to both sides, and we would get 5x equals 5, divide by 5, and we get x equals 1. So if x is 1, my denominator will equal 0. And you can try it and see. If you plug in a 1 here, you get 5 times 1 is 5, and 5 minus 5 is 0. We don't want that. So when we're writing our domain, what we need to say is that every x works except for 1. So I'm just going to write that x cannot be equal to 1. And that's all I have to do to write my domain. This second one over here is actually going to be easier. If you remember, in the last slide, we went ahead and factored this. So let's go back and look. When we're factoring a quadratic, really what we're doing is we are setting it equal to 0 in order to find the x-intercepts. So let's go ahead and look at our final answer here. So what we did is we set this quadratic equal to 0 here, here, and here in order to get our factors. Remember that if we want to find the x-intercepts, all we have to do is take each of these, x plus 3 equals 0, and solve for x. So in this case, x would be negative 3. Take our second one, x minus 2 equals 0, solve for x, so x would be positive 2. Those two numbers will cause this quadratic to equal 0. And again, you can try that. Negative 3 squared is 9. 9 plus a minus 3 is equal to 6, and 6 minus 6 is 0. We can't have that. Try the 2. 2 squared is 4, and 4 plus 2 is 6, and 6 minus 6 is 0. Again, that won't work. So we really did most of the work to figure out our domain on this one. We know that x cannot equal negative 3, and x cannot equal 2. So let's go ahead and write that. And there we have our domain. So what does this look like graphically? What do rational expressions look like if we graph them? And let's look and see how this domain is working out. So we said, and I'm going to go ahead and write that down, that x cannot equal a -3 and x cannot equal 2. Here's what this expression looks like graphically. What's interesting about this graph is notice there's a space in between these two lines, or these two curves. In fact, if I were to take and draw a dotted line, let's go ahead and do that, between these two curves, it would be about right here. So it looks like this blue line is coming up and getting really, really close to this orange dotted line, but it's never actually going to reach it. Same thing with down here. This orange dotted line is really close to this blue line down here, but this end behavior down here, it's never going to reach it. Let me draw some arrows so you know. So this end is never going to reach the orange, and this end is never going to reach this orange dotted line. What we call this orange dotted line is an asymptote, and you'll study that when you start to graph these. But for now, let's look at the relationship between our domain and this asymptote. And notice in purple here it says, excluded factors that remain in the denominator after simplifying become asymptotes. So if we go back and we look at our simplification of this, we ended up with 3 over x plus 3. So let's go ahead and write that down. So we ended up with 3 over x plus 3. This is a factor that remained in the domain. Notice that at x minus 3, so here's 1 right here, and then we have 2, and then 3 is right where our asymptote is. This is where our asymptote is. This is the factor that remained in the domain. Now, if you're wondering what happened to our other factor that's no longer around, if we have a factor that gets eliminated, what we end up having on our graph is a hole. And you can't see it when you graph it on a regular graph, but what you should know is that x cannot equal 2. So right here, where there's a 2, there's actually a hole there. And we won't get into that any further, but I just wanted you to understand why x cannot equal -3 and x cannot equal 2. Okay, let's go back to our simplifying, since that's the main reason for this lesson. Let's actually do 2 more. Go ahead and pause the video and you try these, and then come back and see if you did them correctly. Okay, so hopefully when you come back and you look at this first equation, you have figured out that you need to factor out a GCF of 3x, so you're left with x minus 3. The bottom cannot be factored, so we still have x minus 3. If we eliminate the things that are in the denominator and the numerator, we can eliminate the x minus 3, and we're just left with 3x on top. And that is this rational expression simplified. Okay, let's do the last one over here. So in my numerator, you should have factored out a 6 and been left with x plus 2. And then in the denominator, we have a quadratic. So hopefully you made your x, and in the top of your x, you did 2 times 6, which was 12, and in the bottom, you did 7. And then you put a 4 and a 3 here. 4 times 3 is 12, and 4 plus 3 is 7, in order to factor out our quadratic. So then if we go ahead and write our quadratic with the middle term expanded into 4x plus 3x, we get this expression. If we group, then we can factor out a 2x from our first group and get x plus 2. We can factor out a 3 from our second group and also get x plus 2. So in our final 2 groups, we can see what we have. We have x plus 2, and then what's left is 2x plus 3. And that's what we'll go ahead and write as our denominator up here. So we have x plus 2 and 2x plus 3. Now all we have to do is eliminate anything that's in our numerator and in our denominator, and that would be x plus 2. So our answer here is going to be 6 over 2x plus 3. Now let's go ahead and finish this problem by writing the domain. So remember that all we have to do is figure out what would make the denominator equal 0. And in this case, this is pretty easy. X cannot equal 3. So I'll go ahead and write x cannot equal 3. If we put a 3 here, 3 minus 3 is 0. In our second one, we've already factored it into x plus 2 and 2x plus 3. So if we want to know what's going to make this be equal to 0, remember that all we have to do is take each factor, set it equal to 0, and solve. So if we set x plus 2 equals 0, x will be negative 2. So x cannot equal negative 2. In our second one, we have 2x plus 3. If we set that equal to 0, we would subtract 3 from both sides and get 2x equals negative 3. We would divide both sides by 2, and then we would find out that x cannot equal negative 3 halves. So in pink here, these are our domains. In this first problem, x cannot equal negative 2 or negative 3 halves. And in this first problem here, or this is our second problem, in our first problem here, x cannot equal 3. Okay, that concludes our lesson 1, simplify rational expressions and find the domain. So at this time, you should be able to factor both the numerator, the denominator, and eliminate things that are in both in order to simplify. You should also be able to look at the denominator and determine what makes this equal 0 in order to define our domain.